u1 sine. And then I've got cos x times u2 plus cosine of x times u2. And what was u2? This mess over here. It's the sine of x minus the log secant plus tangent. Okay. I think I get a cancellation over here, right? With the minus sine cosine plus sine cosine. So the particular solution wants to be of x. Minus sine cosine get canceled. I get minus cosine of x times the logarithm of secant of x plus the tangent of x. Let me just check that that's correct. Yes, it is correct. Okay. So what's the general solution for the differential equation y of x? Remember, that theory is always the same. It doesn't make a difference if it's variable coefficients, constant, or the right-hand side is a finite family or not. Because it's a linear inhomogeneous equation, the most general solution is the sum of the homogeneous solution, which is c1 sine plus c2 cosine, or yc of x. Which one did I switch first? It doesn't make a difference, that's might be consistent. c1 sine x plus c2 cosine x. And then you got the particular solution, which is minus cosine of x times the logarithm of secant of x plus the tangent of x. Okay? And now I think you can appreciate why I said that if you have a differential equation that has constant coefficients and the right-hand side is finite family, you want to use method of determining coefficients. Okay, a lot of work going into this. Well, the other one has a little bit of algebra, but and again, it depends. I mean, I'm sure I could cook up a problem where the algebra involved in undetermined coefficients is more than in the method of variation of parameters. But in general, the rule is that if you have a differential equation that's amenable to constant coefficients and right-hand side finite family, use the method of undetermined coefficients. Okay, still have some time left. What I'm going to do now is present the general result, okay? What happens is that, just kind of, most of the equations that occur in practice are second order, and imagine just doing this over and over and over again, okay? For different coefficients, different right-hand sides. It'd be nice if we had a formula that would work for any second order equation, okay? And I'm going to do that now because it's in the book. And then what you can do when you do the homework is you just plug into the formula. But again, any formula that you develop has a certain assumptions in it, a certain form, okay? For example, remember when we did reduction of order, okay? That's probably the most recent one that we did. We had to put in the form, y double prime plus, made the coefficient equal to 1. And then we had this general formula for the second solution. The same thing over here, okay? I'm going to take a general second order linear equation, no restriction on the coefficients, okay? And no restriction on the right-hand side. But I'm going to write it y double prime. But you always can do that, right? Because you have a second order equation, just divide through. But you have to remember, what a lot of students make a mistake on is they'll look at the formula, they'll plug in, and they forget, oh, wait a minute, the formula is derived under the assumption that the coefficient of y double prime was 1. And all you have to do is just divide through, okay? So let's start with that. And you can see all this stuff now generalized to a arbitrary equation. The u1 and u2 will drop out just like it did in this problem over here. It wasn't something that is peculiar to the equation that I chose because I made this y double prime plus y, or I made this tangent of x. Okay? The general, it's amazing how the technique will work in general. Okay? And for an exam, at the end, I don't want you to memorize formulas. On the exam, I would give you a cheat sheet that would have these formulas on them, okay, for this one. Just like superposition, I don't want you to have to memorize that. Okay, so we'll probably just get to derive that today, and that'll be it. Okay, so let's consider the most general second order equation that you can come up with that's linear. It's going to be the second y with respect to x, right? Now choose a notation like we did before, P of x dy dx, right? Plus Q of x y is equal to some function f of x, right? Certainly the equation that we had before, forgot what it was it y double prime plus y equals tangent is of that form. And notice over here, I don't make the assumption that it has constant coefficients. P of x, Q of x, okay? Now if you said over here, wait, suppose I had a coefficient over here of x cubed, just divide through, okay? You always can do that. So any second order linear equation, regardless of what the coefficient of y double prime is, can always be put in this form. So what you have to remember though is that when you apply the formula that we'll ultimately get to, you have to first put your equation in this form. Then you can just plug it. Okay. So we have to start off, okay, you solve the homogeneous equation first. So assume y1 of x comma y2 of x are linearly independent solutions to the homogeneous equation. And we'll again use our notation L on y is equal to 0. Maybe I'll put L on y over here, okay? L on y just means that. And that's what we always did, right? The first step was what? You shut off the right-hand side and you solve the homogeneous equation, okay? We're focusing now on getting the particular solutions. So let's not worry about getting the homogeneous, okay? We know how to do that in certain cases, okay? So therefore, you solve the homogeneous equation, okay, and I get these two functions, y1 of x and y2 of x, both of which are solutions to the homogeneous equation. 2, like we did in that particular problem, okay? This is called the variation of parameters. This is like the general case. Okay? And again, reason it's called variation of parameters. Instead of doing C1y1 plus C2y2, which would be the solution of what? The general homogeneous equation, I'm going to replace those by unknown functions of x. u1 of x times y1 of x plus u2 of x times y sub 2 of x. Okay. I have to solve for u1 and u2. Well, we know what we have to do. We've got to plug in there. So what's the first derivative? yp prime of x. Using the product rule, it will be u1 prime of x times y1 of x plus u1 y1 prime, right? Plus u2 prime of x, y2 plus u2 y2 prime. Just use the product rule. That's all I'm going to do. Okay? Okay? Now, impose constraint, just like I did before. What was the constraint I imposed in the last problem? Is everything with the derivatives should go to 0, right? Impose constraint. Okay? I want to get rid of this guy. Now, not separately, but together. I want y1 u1 prime of x plus y2. Where's the other prime? Yeah, y2 u2 prime of x to equal 0. Again, we'll have to come back to that, so let's put a little red box around that. That's my constraint, okay? Well, when I make that constraint, the y1, u1 primed, okay, I kind of basically can forget about that. And the y2, u2 primed, where's that? Here it is, right? And now I just have u1, y1 primed and u2, y2 primed. Great. Well, that's yp double prime now. That's all I need. Let's use the product rule. Okay, that one I don't need. I have u1 primed, y1 primed, right? Plus u1, y1, second derivative, just using the product rule on u1, y1 prime. Okay? And then same on that, plus, now I need u2 prime to y2 prime, right? Plus u2, y2 double prime. Okay. Now what I'm going to do is plug in for all my derivatives on the left-hand side, simplify, and amazingly what's going to happen is I'm going to show you that the coefficients of u and u2 go to 0, just like it happened in the other example. Okay, L operating on Y particular. Okay, I need what? I'm doing over here, right? YP double prime. So U1 prime to Y1 prime. Plus U1 Y1 double prime. Plus U2 prime Y2 prime. Then I need U2 Y2 plus, what's the second term of the equation? P of x. Now I need the first derivative, yp prime. U1 Y1 prime. Plus U2 Y2 prime. Plus Q of x times what? Times y. U1 Y1 U2 Y2. Okay, let's clean this up. L operating on Y particular. Okay? Let's get the coefficient of U1 of x first. Okay? Let's get all those U1 coefficients. Okay? Here I pick up a Y1 double prime, right? P of x, Y1 prime. Right? There's a U1. And finally, I get a Q of x, Y1. Plus, let's get the coefficient of U2 of x. There's a Y2 double prime. P of x, Y2 prime. Plus finally, a Q of x, I'm looking for U2 coefficients, Y2. Plus, and let's see what the residual is. I've got Y1 prime, the derivative of U1 with respect to x. Right? That one I took care of. Then I get this guy. Plus Y2 prime of x, which I know. The derivative of U2 with respect to x, which I don't know at this point. That I took care of. That and that I took care of. That's it. That's L operating on YP. Okay. Now, look at the coefficient of Y1, of U1 rather. Y1 double prime plus P of x Y1 prime plus Q of x Y1. Didn't I say that Y1 is the solution to the homogeneous equation? Right at the beginning. Y1 and Y2 are both solutions of the homogeneous equation. So therefore, Y1 double prime plus P of x Y1 prime plus Q of x Y1 equals 0. And the same thing for Y2. So this whole thing is equal to 0. That whole thing is equal to 0. So it comes out that L operating on YP is just simply two terms. Y1 prime, U1 prime plus Y2 prime, U2 prime. And we know that L on YP has to be a solution of what? Of YP rather, has to be a solution of the inhomogeneous equation, so that equals f of x. And I'll block that one up, and I'll do our second equation. Okay. So, we started with this equation, okay? We first construct y1 of x and y2 of x. Those are solutions to the homogeneous equation. And then we assumed a particular solution of the form known homogeneous times what? An unknown u1 of x plus the second known solution of the homogeneous times u2. And now we get this following system. Let's put these two ready boxed equations together. I now have a system. y1 of x, which I know, the derivative of u1 with respect to x, plus y2 of x times the derivative of u2 with respect to x. Right? y1 u1 prime plus y2 u2 prime is equal to 0. And the one which I just derived over here, which says that y1 prime of x, remember the y1 and the y2 are known. So I know this guy. Here's the u1 x derivative plus y2 prime, the derivative of u2 with respect to x. And now, of course, this is equal to f of x. So you're going to get two equations on two unknowns, u1 prime, u2 prime. Okay, you can use linear algebra or any way you want to eliminate them and you integrate. Okay? And again, just to emphasize, again, for those who have linear algebra, what this really is over here is we've got the Wronskian over here, right? We've got y1, y2, y1 prime, y2 prime, and that's by definition, if you look back, the Wronskian, times the vector du dx, which is the column u1 prime, u2 prime, that equals 0 f of x. Just putting in the matrix notation. Okay? Okay, now I just want to complete this. I usually just stop at this point, but the book actually goes a little bit further. Let's actually solve for u1 prime, u2 prime, okay? And then we'll call it quits. Okay. Now I'm just going to use the term, like I said, there's a lot of different ways to do this. I'm just going to give you know how to solve two equations, two unknowns, right? Okay? Let me just tell you what happens now. The derivative u1 with respect to x, I'm pretty sure is just minus y2 of x, f of x, over the Wronskian. I'll tell you that in a second. And the derivative u2 with respect to x is equal to y1 of x, which you know, f partial, f of x. Let me just check this over the Wronskian. That's why I don't want you to memorize, because, okay. u1 prime is minus y2f over the Wronskian. Don't forget that minus sign for the first one. And u2 prime equals y1f over the Wronskian. Okay? Where w is just this determinant. y1, y2, y1 prime, y2 prime. Again, for those who don't have linear algebra, it's y1, y2 prime minus y2, y1 prime. Okay? Okay? So when we come back on, where's today? Today's Monday, yeah, we'll have class Wednesday.